Hello everyone, welcome to the mechanical vibrations tutorial. Today we are going to continue on the interesting example that we have in the previous tutorial, which is the two identical pendulum case. But today we are going to find the system response and also discuss a very interesting topic in the vibration, which is the beating phenomenon. So let's begin. So this is the problem statement that we had last week, and I added more items to it, which is items C and D, which are new for today's tutorial. So first we wanted to find the equation of motion, natural frequencies and mode shapes. Then we want to find the response of the system based on the initial conditions that are given here. And finally, we want to find the conditions that give us a beating phenomenon. We're going to discuss beating in detail and you will see how interesting this phenomenon is. Okay, so let's go very fast to part A and B of this problem. So if you want to find more details on that, we can check the previous tutorial. So we found the equation of motion for this system as ml squared theta double dot 1 plus mgl plus kd squared theta 1 minus kd squared theta 2 equal to 0. And this is theta 1 and that one is theta 2, and I actually gave a very detailed discussion on that in the previous tutorial. And we also have ml squared theta double dot 2 plus mgl plus kd squared theta 2 minus kd squared theta 1 equal to 0, right? And we will be able to set it into the matrix, like this is theta double dot 1, theta double dot 2 plus whatever the theta 1 and theta 2, and we set it equal to 0. And then we selected theta I as theta I cos omega t plus phi, right? And then we found the natural frequencies and the mode shapes, right? So I just want to present the the expressions for the natural frequencies and the mode shapes. So as you may remember, we found omega 1 squared equal to GL and omega 2 squared equal to GL plus 2k d squared divided by ml squared. How we found it? We found the characteristic equation from the matrix representation, and then we set the determinant equal to 0, right? And for Ri, which is the amplitude ratios, we found it's equal to kd squared divided by mgl plus kd squared minus ml squared omega I squared, where I is equal to 1 and 2. For R1, which is for the first mode, we found the amplitude ratio of theta 2 1 divided by theta 1 1 equal to 1. And for R2, we found theta 2 2 divided by theta 1 2 equal to minus 1, right? And finally, we set the response of the system as the summation of the two modes. So we had theta 1t equal to theta 1 1 cos omega 1t plus phi 1 plus theta 1 2 for the second mode, cos omega 2 plus theta 2. And for the other mode, or for the other mass, or the mass in the right hand side, so theta 1 is for this one and theta 2 t is also very similar. We can use r1 theta 1 1, right, cos omega 1t plus phi 1 plus r2 theta 1 2 cos omega 2t plus phi 2. So these are the things that we found before, and we can simply basically know how we derive them based on the discussion we had before, right? Now in part C of this problem, we want to find the response of the system based on the initial conditions given in the problem, right? And what are the initial conditions here? We got theta 1 0 equal to A, and A is just a constant, and the rest of the initial conditions are 0. So theta 2 at 0, theta dot 1 at 0, and theta dot 2 at 0, they are all equal to 0, which means there is no initial amplitude and initial velocities for the second mass. Also the speed or the velocity of the first mass is equal to 0, right? So the whole is equal to 0, right? So these are the initial conditions. So if we basically use the definition we have for theta 1 and theta 2, what are the responses we have? So we got theta 1 equal to theta 1 1 cos omega 1 t plus phi 1 plus theta 1 2 cos omega 1 actually omega 2 t plus phi 2. So theta 2 r1 is 1, so we get theta 1 1 cos omega 1 t plus phi 1 minus theta 1 2 cos omega 2 t plus phi 2. Why minus? Because r2 is minus 1. So if we take the derivative, we got theta dot 1 equal to minus omega 1 theta 1 1 sine omega 1 t plus phi 1 minus omega 2 theta 1 2 sine omega 2 t plus phi 2, right? And theta dot 2 is equal to minus omega 1 theta 1 1 sine omega 1 t plus phi 1, and minus times minus plus omega 2 theta 1 2 sine omega 2 plus phi 2, right? So I want to go step by step, and then you will see how we use the initial conditions to find basically our unknowns. So what are the unknowns here? Theta 1 1, theta 1 2, phi 1, and phi 2. Same thing repeated in other equations, and we have 4 of them, and we have 4 unknowns. So let's set t equal to 0 in all these equations, because it shows the moment that t equal to 0, and use these numbers like a and 0 for all these 4 equations. So let's do that and see what we get. So now if we do this, we have a is equal to theta 1 1 cos phi 1, because t is 0, right, plus theta 1 2 cos phi 2, 0 equal to theta 1 1 cos theta 1 minus theta 1 2 cos phi 2, right? 0 equal to minus omega 1 theta 1 1 sine phi 1 plus minus omega 2 theta 1 2 sine phi 2, and 0 is equal to minus omega 1 phi 1 sine phi 1 plus omega 2 phi it's actually theta, so let me do it again. So we have theta 1 2 sine phi 2, right? So how can we find these 4 unknowns? Let's take a look at these 2 equations first. So if I take say for example one like this one and this one to the right hand side, to the left hand side, what would we get here? So if we do this, we have omega 1 phi 1 1 sine phi 1 is equal to minus omega 2 phi 1 2 sine phi 2, and this one gives us omega 1 phi 1 sine phi 1 equal to plus omega 2 phi 1 to sine phi 2. So if we compare these two equations, what do we find? So these are identical. One of them is equal to minus of this, the other one is equal to plus of this. What does it mean? The only thing that is valid is all of them are 0, right? 0 equal to minus 0 or 0 equal to plus 0. However, we know that to make all of them 0, for sure these values are not 0. There is amplitude of vibration and there is a frequency of vibration. So the only thing that satisfies this condition is the sine of phi 1 to be 0 and the sine of phi 2 to be 0, which means that phi 1 and phi 2 are equal to 0. We always look for an angle from 0 to pi, right? So we use 0 here. So this is very easy, right? We actually found two unknowns very easily, and this gives us that phi 1 equal to 0 and phi 2 equal to 0, right? Makes sense. Now we use this values for phi 1 and phi 2 in these two top equations, and we know that cos of 0 is equal to 1. So let's see what we get here, right? So we have, this is 1, or let me use the previous one. So if we set that 0, so this is 1 1 1 1 1, and I'm sure you can simply make some calculations to find theta 1 1 and theta 1 2, right? So if we do this, we have basically A is equal to theta 1 1 plus theta 1 2, and 0 is equal to theta 1 1 minus theta 1 2. This is a very simple system of equations that we can solve, and if we do that, just take this to the other side and you can simply solve it. You can find theta 1 1 equal to A squared, right? And if we do this, we can find theta 1 2 equal to A, the A divided by 2 as well, so half of A. So they are actually equal, right? So it makes the the final response of the system very easy. So we get theta 1t, the final response that we were looking for. We have A squared, and I can factor out A squared because theta 1 1 and theta 1 2 they're equal, or they're identical here. We found that. So we have A divided by 2 cos omega 1 t, and phi 1 and phi 2 are equal to 0 plus cos omega 2 t. This is the first response of the system, or the response of the first mass, and theta 2 t is equal to A divided by 2 cos omega 1 t minus cos omega 2 t. Interesting, right? We found the response of the system as the question requested, right? So now I want to start discussing the beating phenomenon, but before we continue on that, basically going forward with the beating phenomenon, I want to review some or remind you some trigonometry relationships. So if you may remember from calculus, so we know that cos alpha, and alpha is any angle, plus cos beta, we can convert this summation to a multiplication, is equal to 2 cos alpha plus beta times, or we can put the whole thing in here, times cos alpha minus beta divided by 2. I'm sure you could find it in many calculus books, or in our videos in this channel on the calculus, right? Or differential equations. So we also have cos alpha minus cos beta, which is equal to minus 2 sine alpha plus beta divided by 2 sine alpha minus beta divided by 2. Why I'm doing this, or I'm showing these two equations? I want to apply them in these two equations, right? So if I do that, if I use these two formula, and for here alpha is omega 1 and beta is omega 2, what would we get? Let's do this and use this formula. We get theta 1 equal to A cos omega 2 minus omega 1 divided by 2 times t, because t is in both equations, times cos omega 2 plus omega 1 divided by 2 t, and theta 2, the second mass, response, is equal to A sine omega 2 minus omega 1 divided by 2t. And why the negative sign from the formula we showed disappeared? Because we set it inside and we have omega 2 minus omega 1, right? If we want to have that negative sign before A, we have omega 1 minus omega 2. So we know that omega 2 is larger, so we just put it inside. Times sine omega 2 plus omega 1 divided by 2 times t. So this is the response of the system after we set it into multiplication. Okay, so now let's say what is beating phenomenon. When we have a response, of a system that is a combination of two harmonic functions, and the frequency of the two harmonic functions are near to each other, the beating phenomenon occurs in the system. So it means that if, for this case, if omega 1 and omega 2 are close enough, then we're gonna have beating in our system. And basically the beating is not necessarily in a 2 degree of freedom system. It could also happen in the force vibration of undamped systems, because in the force vibration of undamped system we have, say for example, anything like xt was the response we found was the summation of the homogeneous part and the particular part. We would get A, say for example, sine omega nt plus B, say for example sine omega t, and then we could put them together. Or let's say if we use cos, it's gonna be exactly same as what we have here. Then we would have cos omega nt plus cos omega t. So we could simply use above formulas and combine them. So I will just raise this point that the beating is not necessarily for a 2 degree of freedom system. It could also happen for the vibration of an undamped system under a force vibration. So in that case, if omega and omega n are close enough, then we get a beating phenomenon. So what happens when the system is under a beating phenomenon? So for this case, if omega 2 and omega 1 are close to each other, or the value of them are near or similar to each other, the response of the system, for example for theta 1, would be something like this. Interesting, right? So sorry for my drawing. So the response, say for example for theta 1, right? If we have a beating phenomenon, the response would be something like this. And what happens is the response is like follows also a sort of harmony. The increase and decrease of the amplitude is also following harmony. So one of the frequencies are basically associated with this one. However, the two frequencies combination is also associated with this one. So for example, for a forced vibration, this one, say for example for a forced vibration when we have omega and we have a natural frequency of omega n, this, like the period, is gonna be 2 pi over epsilon, where epsilon is equal to, or 2 epsilon is equal to omega minus omega n. So as long as omega and omega n are similar, but let's say are not very different, right? Are not very different. So for this case, we also have a beating. And for a 2 degree of freedom system, when we have the natural frequencies close to each other and we have the combination of 2 harmonic functions like this, like what we found here, then we have a beating phenomenon in the system. So remember, when the response of a system is the multiplication of 2 harmonic functions and the frequencies of the 2 harmonic functions are near to each other, then we can say that a beating phenomenon occurs on the system. For this case, let's see what the condition is. So we found omega 1 squared equal to GL and omega 2 squared equal to GL plus 2k d squared ml squared. And what was the question? Part D of the question, the condition for beating, right? And the condition for beating, which means that this part of omega 2 should be small enough so that omega 1 and omega 2 are close enough, right? Interesting. So if we want to, or basically when we compare to omega 2 to 2k d2 over ml squared must be much smaller than GL, because GL is here and there. So when they want to, omega 1 and omega 2 want to be close to each other, this part should be small enough compared to G over L. So that's the condition. This is the condition that we need. If we further simplify it, because we already suppose that, say for example, M is known, D is known, L is known, and K is our design parameter, we can do some cross multiplication and simplify for K. So K must be much smaller than MGL divided by 2D squared. So say for example you have a design problem, you want to design K for this double pendulum case, that the beating phenomenon occurs in the system, or the response of the 2 masses follows a beating behavior. The condition on K should be like this, like what we found here. Very interesting, right? So this is the condition on K, which gives us a beating phenomenon. And I showed you the beating is like this. And actually beating is very important in many vibration or acoustic problems, in sounds and other types of waves like vibration. You should know that beating is very important to be investigated. So now for this system we found the condition that gives us the beating phenomenon, right? I hope you enjoyed this video. We finished this example, and in the next tutorial we're gonna discuss another interesting topic in the 2 degree of freedom systems. So thank you and stay tuned for the next videos.